value is at low frequencies. This is frequency across here, logarithmic scale. The low frequency amplitude ratio ought to be the gain of your system. That's equal to K. So this is another way of determining K. From here on out, this is the K that's going to be more reliable than those others you've gotten already. We're going to stick with this more than likely. Then this thing down here, the lower graph, is a phase angle. And there's some frequency at which it is negative 180. This frequency right here, if this is a frequency of 1.9, 0.7 is the frequency, and we call that the ultimate frequency. Everybody say ultimate frequency, Dr. Henry. Ultimate has 3 syllables. Frequency has 3 syllables. That's 6 syllables you had to say to convey to me that that was the ultimate frequency. So we have a shortcut for that. We call that F subscript U. So everybody say F-U, Dr. Henry. Pardon? And the units of that are cycles per time, either cycles per second or cycles per minute. And that is a very important number. There's something else that's important. Oh, then where that FU line crosses the data line, you come over here and you get the value of this amplitude ratio and take the reciprocal of it, and you will get KCU. That doesn't have much meaning. It's the ultimate controller gain. And we haven't even talked about controllers in here, have we? I don't think we have. But we're going to design a controller. And that number is going to be very important in designing a controller. We're going to be doing that in a couple of weeks. So this is a beautiful experiment to find out the ultimate frequency, the ultimate controller gain, and you can also find out the order of the system if you want to, but let's not worry about that. Graph these in MATLAB and get 100% bonus. Here's a quote from the book that was used some years ago, first edition of it. The study of how the amplitude ratio and phase angle vary as the omega frequency varies is an important part of automatic process control. Any questions on that? For those of you who are not the alternate method, I want you to do this and turn in this graph here for your system in your region by noon Monday. I think it says that down here at the bottom noon. Date due date and time, week 7 at noon. All right. What if you have the alternate method? We use something that's called the relay feedback, and it makes this kind of input that's, you might call it square wave, but it's, nevertheless, it goes up and down. And this is the output. And from that graph, you can determine the gain of the system, the time constant of the system, and the dead time of the system. Let me run an experiment doing that. Relay. I'm going to use pressure again. I'm going to run this for 15 seconds. I'm going to put in a very large value for controller gain. And you see, you had somebody, who was talking that had the closed, number one was open all the time? And number two was closed all the time? I'm going to run this and see what happens. Relay means it goes up and down. We'll see this in a minute. Okay. This is the value that I want. Something's weird here. Let me try this again. See what happens this time. I'm going to change my set point to 12. Run this again. What's your set point here? Well, that might be the wrong value, but let's see what happens. That's what I want. 12 is the set point. When the set point, when the output, which is the red, is above the set point, the input drops down to the floor. And when it's below the set point, the input jumps up to the ceiling. And analyzing this graph will allow you to get the gain, the dead time, and the tau for the system, and case it. So let me show you a better one. Let me put the, so actually you may have to do some experimenting a few times to get the best values for that. But it'll pay off. See what happens here. Oh, while we're waiting,